Alright, so by far the hands-down favorite of the most confusing topic from our last lecture was the idea of first, second, and zero-order reactions, the enzyme kinetics portion, or reaction kinetics portion of the lecture. So I'm just going to take a little while here and explain that again in a little bit of a different way, hopefully, and make it clearer for everyone in the class. So let's consider a very simple reaction where two reactants, A and B, come together to form product, P. Now, if you can imagine, if we have two of these reactants, let's say 5 molecules of each, 5 molecules of A can be glued to 5 molecules of B and make 5 molecules of product. If we want to make more product, or if we want to make product faster, we can increase the number of A and B. We can say that 10 molecules of A and 10 molecules of B will give us 10 molecules of product. So we get more product and we get product faster. This is a second-order reaction because two things need to be changed to influence the kinetics of the reaction. Said a little bit differently, the concentration of A and the concentration of B need to be changed simultaneously in order to increase the rate of the reaction. So it's second order. We can convert the second-order reaction into a first-order reaction by putting one of the reactants in excess. So let's imagine we have 10 molecules of A and 1,000 molecules of B. We can, in a given unit of time, make 10 molecules of product. The reason why we can only make 10 molecules of product is because A is limiting. A slows this reaction down. A causes less product to be made because A is limiting. So now we're looking at a first-order reaction because B is out of the picture. If we add even less A, we will in turn make less P. Likewise, if we add more A, we will make more P. We can do the same exercise with B. If we add less B, nothing really happens. If we add more B, 1,010 molecules, again, there's no change in the rate of the reaction. Because B is so much in excess over A, B is really not influencing the rate of the reaction at all. It's all controlled by A. So this is now a first-order reaction. We're talking biochemistry, so now let's add just one more wrinkle to the story here, and let's say that this reaction must be catalyzed by an enzyme. And this enzyme has some rate of catalysis. It can only make, we'll say, 10 molecules of P per second. If we have 5 molecules of A and 5 molecules of B, in 1 second, we will make 5 molecules of P. Half of the enzymes will go to work and the other half will not. If we add 8 molecules of A and 8 molecules of B, the enzymes will work on those, the reaction will occur faster, and the amount of P will go up. It's a second-order reaction. If we have 10 molecules of A and 1,000 molecules of B, we will make 10 molecules of product. And so now we're at a first-order reaction. Add less of A, and the amount of P will go down. The amount of product, the rate at which product is made, is controlled by the levels of A. But let's say that we have both A and B in excess. We've got 1,000 molecules of A around and 1,000 molecules of B around. But our enzyme can only process those reactants at 10 molecules per second. After 1 second's time goes by, we will only make 10 molecules of P. It is the enzyme that is limiting our reaction. Decrease the amount of B, no change, because the enzyme is limiting. Decrease the amount of A, no change, the enzyme is limiting. Increase the amounts of both. It doesn't help you, because the enzyme is limiting. And so because it is the enzyme that's limiting this reaction, and the concentration of all of the reactants play no role, this is a zero-order reaction. It is a reaction where neither the concentration of reactant A nor the concentration of reactant B is playing any role in the rate of the reaction. The rate of the reaction is controlled solely by how quickly the enzyme can catalyze the reaction, but since the enzyme is not a reactant, this is a zero-order reaction. So hopefully this helps to clarify some of the concepts both around characterizing first, second, and zero-order reactions, but also set us up for what we're going to talk about the next time we meet, which is how we deal with zero-order reactions when enzymes are involved.